Thank you. Thank you very much for this amazing introduction. And there's a lot of friendly faces in the audience, including the person who actually gave me my first job, Shivaji. So thanks to all the friends here. I wanted to basically take you on a journey that basically has to do with sort of topological materials, but not entirely. It's a journey that basically tries to understand or tries to classify materials based on really the only numbers that I fully understand, which are integers. So I'll try to basically convince you that from Mendeleev's time to really even the new moire materials, we can classify states of matter best, or at least some of the states of matter best, the materials best, by retorting to the rigidity of the integer numbers. So I'm going to make a disclaimer, since it's a public talk. We don't have in my field very beautiful pictures such as the universe or wormholes or even biology. But we do have these type of material pictures where basically you're trying to figure out how material is formed. So the field, in that sense, is not really prone towards amazing public lectures, but I'll try to convince you that there's an underlying theme in understanding quantum materials, and that theme keeps surfacing from antiquity to today, and that theme is basically believing in the power of integers. And if you really believed in the power of integers, maybe quantum mechanics could have been discovered in the 1800s. So what does my field try to, condensed matter physics, what does my field try to do? Well, it tries to understand really what the world is made of. And moreover, tries to understand what we can make, what kind of materials can we make, and more generally what kind of phases of matter you can make in the world. Now, of course, starting off very early on, the Greek philosophers started asking these questions, and they gave some sort of a garbled answer to what the world is made of. There's 4 classical elements, and then Aristotle, which are given here by Empedocles, and then Aristotle basically brought about ether, which was supposed to be kind of the air that the gods breathed. And by the classical period, by the late classical period, this was philosophical common stock in the Mediterranean area. Of course, as I said, it was kind of garbled. Then the next advance of material science, really, if you can call it that way, was basically alchemy. And alchemy, this is kind of where the word comes from, but basically it appears centuries later from Aristotle in the Hellenistic Egypt with concepts from the Aristotle framework. Basically, the reason why alchemists thought that they can transmute lead into gold has to do with the fact that they really were thinking that all these elements are made out of the 4 constituent elements, and love and strife, which are supposed to mix or separate elements. So basically, alchemy has this mystical origin, and really the Roman Empire had a kind of a skeptical and even punishing attitude towards alchemy. So it kind of died off in the Roman Empire. Pliny the Elder basically thought it was magic. But then it came back, it survived the Muslim world and came back to Europe afterwards, and didn't produce many things except for the things that were already, iron ores, etc. They were already in nature until 1250, where the first isolation of arsenic by alchemy. Now, really, alchemy is really known for producing 2 elements. One of them being phosphorus, and that's by Henning Brandt, which is also known as the man who put the P in phosphorus, because by the time kind of his first wife died, he basically had diminished all her wealth to 0. He married a second wife, which allowed him to pursue the philosopher's stone, which is obviously something that doesn't exist. And being obsessed with, as all alchemists, with urine, he basically heated up 5,700 liters of urine and then put it into an overheated container, and then at some point glowing fumes started. Basically, phosphate became phosphorus, and he took it, put it in a jar, and it continued to glow off, which is the phenomenon of chemiluminescence. So that's about how we are at the 1600s, 1700s era. But then basically a new method, which is really the beginning of modern chemistry, started. And this new method is obviously the scientific method. And the scientific method, of course, rests on many things: reproducible measurement, peer review, experimentation and controls. But it really required a repudiation of the Aristotelian beliefs. So, centuries later, Bernard Russell, basically, who was a very, very anti-Aristotelian person, basically said that ever since the beginning of the 17th century, almost every serious intellectual advance has had to begin with an attack on some Aristotelian tenet. Now, that's not my favorite quote by Bernard Russell against Aristotle. My favorite quote about Bernard Russell against Aristotle is the one here. It doesn't have really to do with this talk, but it's very, very funny, I think. So, the dawn of chemistry and the departure from alchemy brought about huge advances. So, by the time alchemy was dead, only 2 materials were known. But by the time Mendeleev made his famous table, there were 63 elements there were known. And these elements were, lithium, beryllium, nitrogen, oxygen, etc. But the fundamental thing that Mendeleev did, and the thing that the scientific method brought about, is prediction. And there were many other people who were discovering periodic tables of elements that are not known. And the reason why they're not known, or not as famously known as Mendeleev, is because they didn't predict new materials. Mendeleev saw, after he put his periodic table in order, he saw gaps in his periodic table, and this allowed him to predict new elements. Now, I first obviously want to argue, and this is not really an argument, but something known, that the development of the scientific method and this periodic table really showed for the first time the power of integers in the world around us, just beyond mathematics. This was not fully understood at the time, but if people had taken it more seriously, then you would have, for example, realized that the mass of neutron is the same as the mass of the proton, etc., and you would have basically discovered the neutron much earlier than was discovered, which by this time was not known, even the proton. Now, the advances that basically made integers kind of start to play a crucial role in chemistry started with Cavendish mass ratio in water, which is 1 to 15.9. It's 1 to 15.9 because you really have some isotopes, which were not known at the time, but it's really 1 to 16, right? And then Proust's law basically found stoichiometry, or the fact that elements combine in fixed ratio that are given by integers, and he proposed that small integer fractions are very important in finding elements. Dalton then basically translated these ratios into a unit of weight scale, and this weight scale has to do with the hydrogen atom, and he said that basically every element has a mass that's a multiple that of hydrogen. Now, that's obviously not entirely true because of binding force, etc., but it's almost true. And then Newland basically saw that elements, at least below the D shell of the periodic table, or what was later known as the periodic table, have some 8 periodicity. They're periodic in terms of their chemical reactions, etc., with a period of 8, which is obviously a quantum mechanical statement that we'll come back to later. So the early periodic table kind of embodies these perspective. But what is the periodic in? As we argued, that is periodic in integers, and Mendeleev's genius was basically to treat the atomic number z as an integer sequence and put it into an array that's made that has, one second, to put it into an array where, or a two-dimensional matrix where you can spot gaps. And one gap that he spotted was, for example, here. You can clearly see that there's a 16 difference, and this is just because at low atomic numbers, if you add a proton, you add a neutron, and they have roughly the same mass. There's 16 difference in atomic numbers between different elements. And here there was a missing piece. There were many missing pieces. But then the first element that he predicted was this one, which is cadmium. Okay? And so on and so forth. He made basically this just machine learning type of looking at elements and at their masses and at their reactivities. He made it into an integer-based table, which we now know is this periodic table. Now, of course, if you look at the periodic table, this is nothing more and nothing less than integers in 2 dimensions. Each step is an atomic number at 1 proton and 1 electron. And this discrete count basically encompasses chemical behavior. You have, when you go between integers of filled shells, you have complete changes of reactivity from noble gases to metals, etc. And because you can't slip fractionally between 2 integers, it really means that jumps in these integer properties really mean different type of physical behavior. So in fact, this periodic table, as we now know, is nothing else but quantum mechanics, and chemistry is nothing else but quantum mechanics, but with a lot of AI intuition. And it precedes quantum mechanics, obviously, but it can be explained very easily by just counting levels of electrons in an atom. Now you can see that Schrodinger's equation, and everybody knows that Schrodinger's equation describes basically the quantum world around us. Schrodinger's equation tells you that your electrons have quantum numbers. These quantum numbers obviously are also integers. And these quantum numbers in an atom are principal quantum number, angular momentum quantum number, and spin quantum number, etc. But they have a relationship to the orbital shape and the orbital energy. Then, if we want to add fermions in these elements, then we know exactly, to create the periodic table, we know exactly how many fermions we can add in some shells to basically create the element. So, for example, let's try to understand Newland's law of octaves. This is all Newland's law of octaves is basically the filling of orbitals until you reach the d shells. And it tells you that orbitals or elements that are separated by number 8 really have the same reactivity or same properties. The reactivity, of course, it breaks down once you start going to the d shell. You have to add more, but at least for low atomic numbers, it's good enough. And this is just the fact that the second shell, n equals to 2, allows you to have 2 values of the angular momentum from minus, allows you to have L equals 0 and 1, and each angular momentum allows you to have 2L plus 1 projections of it on the z-axis. So you have, for example, for this one, you have just Lz equals to 0, but you have an electron spin, so it allows you to put in 2 electrons. Here, for this one, you can have Lz equals minus 1, 0, and 1, and it allows you to put time spin, so 3 states times spin, it allows you to put 6 electrons. This 2 plus 6 is exactly Newland's law of octaves. Now, this fact that the integers have this unique rigidity that you can't get from one integer to another is exactly the kind of thinking of quantum numbers. And of course, you know, if we took the periodic table more seriously, we could have understood that there's an underlying reason for it. For example, you could have predicted if you knew that, you know, if you add 1 electron, you add 1 proton because of charge neutrality, but the mass increases by 2 of each element, at least for low numbers, because we predicted that there's something else in the nuclei, which is a neutron, which, because the mass increases by 2, has to have roughly the same mass as that of the proton. The integers in my field bring about another fundamental principle, and this principle is that of adiabatic continuity. Basically now we're going to try to go a little bit away from just elements. If you go to physics and condensed matter and phases of matter, the adiabatic continuity tells you that two phases of matter are really the same phase if you can go from one to another by changing parameters very, very smoothly. So if I can go from two phases of matter that are described by some Hamiltonian, if I could go between one and another by just tweaking some parameters in the Hamiltonian smoothly, then they're really the same phase. Now, the converse of that brings in the integers, and it's true. If two phases are separated, if two phases of matter are described by different integers, the fact that you cannot go smoothly between these integers, right? I can never go smoothly between 0 and 1 by adding infinitesimal numbers, unless I'm willing to spend an infinity of time, then it means that two phases of matter that are described by different integers are fundamentally different. And hence it provides a classification. So you can think that the integers also provide a classification for the phases of matter that we have in the world and for the compounds that we have in the world. So let's go through that a little bit. So I hope to have convinced you that modern chemistry is just nothing else but an application of Schrödinger's equation, that the periodic table, you can understand it from modern chemistry by just looking at, the addition of electrons into quantum numbers, which are integers, and really that material science and quantum chemistry are really just in a way related to integers. But what does that mean we can predict materials? And the answer is usually, at least exactly, we can never predict new materials without making approximations. And the reason for this is also quantum mechanics, is basically entanglement. If we try to understand the behavior of electrons in sites, or for example in some lattices, then here I'm drawing the configurations of 3 electrons in 6 sites. And you can see the number of sites, there are 6 of them. Obviously, the real material has an Avogadro number of sites, an Avogadro number of electrons. I can't write them down here. But the moral of the story is that the number of configurations of electrons in these sites, you can immediately see starts growing exponentially. So because it starts growing exponentially, by the time you're trying to look at 50 electrons, then you basically have more configurations than the number of particles in the universe. So a classical computer can't simulate such a material of electrons of 10 to the 23, for example, electrons which is the Avogadro number of electrons that we have in realistic materials. So exact prediction is out of the reach of a computer or of theorists, even though we know the equations that govern the problem, which is Schrödinger's equation. With limited prediction power, basically, condensed matter has had, or at least material discovery in condensed matter, has had a tradition of just being found by experimentalists and also by chemists. And these are things that are either found by mistake or by some powerful chemist intuition, which really works like AI. So for example, superconductivity, which is the one example that I'm going to give here, of course, semiconductors and their influence on chips is also tremendous in our society, but I'm just going to focus here on superconductivity. Superconductivity is one of the most dramatic integer effects. And in this case, the integer is the resistance of the material, which at some temperature drops to 0. And you can ask, how 0 is this 0? Well, I can really measure it. And if I measure it, or if experimentalists measure it, this 0 is 0 to better than any accuracy of your measurement. So for example, you can set up supercurrents in niobium loops, and they go on forever, meaning forever, decades, until you decide to stop them or heat up the material above the transition temperature. So the fact that you can get 0 resistivity and exactly 0 in a material is another emphasis of what I was saying, that integers can describe compounds now rather than just single elements. Of course, superconductivity, I don't need to convince you why it's important. It's important that we have wires that can drive current without dissipation. It's important in maglev trains. It's important in quantum computing. It's important in many things. But this is just one example. And the generalization of a classification to the majority of the compounds that we have in the world presents a challenge. And the challenge is the fact that once I start mixing elements, so elements, I know they're classified by integers, periodic table, stoichiometry is also integers. As we learned, stoichiometric formula is this. Once I start mixing the 93 or 94 elements that are occurring in nature in these proportions, I start getting an embarrassment of riches. For example, these are just the elements in a small part of what is called the kagome metals. These are just the compounds made out of these simple set of elements. There's there's kagome metals that are made out of more elements than this, but this is just one symmetry group, one type of material, one type of elements. And if you start to think about how many elements exist in nature, you go to this ICSD database, which is in Karlsruhe, and you find out there's more than 300,000 compounds made out of the 93 elements in nature, and about 200 are added every month. So the question that we're going to ask now is how to classify, or is there a principle that can classify all these hundreds of thousands of compounds? And this principle that classifies all these hundreds of thousands of compounds has to kind of separate them into some dramatic tensor, or certainly not just a matrix like the periodic table, that basically can tell you whether two compounds are the same or fundamentally different. So the first hint that there is such a principle came, as Paolo mentioned, about more than 40 years ago. And it's really the first example of a macroscopic quantity where a topological invariant is actually measured. So in 1980s, von Klitzing measured this Hall conductance, which is really just measuring the division of the current in the x direction over the voltage in the y direction. You just measure this in a sample under a large magnetic field. The sample looks like this. So I would challenge anyone in the audience to tell me the sample that looks like it's been soldered by somebody who doesn't know how to solder it, and that these are the contacts, gives you this Hall conductance to be good, to be an integer in some units of e squared over h. And this integer is quantized to better than 10 to the minus 12, actually. This is 10 to the minus 9 is for the fractional states in the best cases. This is 10 to the minus 12 for the integer state, and this is an integer, as you can clearly see here. And you can see these plateaus on which this integer remains constant as you vary the magnetic field. So this is the first stunning quantization of a macroscopic quantity besides the zero resistance of the superconductivity. And it's the first sign, in hindsight, that topology can dictate a macroscopic quantity. Now, what is topology and how does it enter? Well, I don't really have the time to go through it, but basically the idea is that when you're solving Schrodinger's equation, you get two things. The Schrodinger's equation has a Hamiltonian, which is really what we do in, at least in my field of physics, is really just diagonalizing matrices. There are these Hamiltonians in some basis. And this Hamiltonian has a momentum, which is the momentum of the electron, and then you're trying to find the energy of the electron versus momentum, which gives you diagrams that look like this. This is, for example, silicon. These diagrams give you the allowed energy levels of the electron as a function of momentum. And they're good because you, for example, want to tune in chips, you want to tune the gaps, you want to tune different mobilities, etc. So you can play around with these gaps and in different materials. But it also gives you the wave function of the electron as a function of momentum. And the wave function of the electron as a function of its momentum, you can think of it as a multidimensional space. The wave function has many components. It's a multidimensional space or a manifold. And this manifold, once we understand that the wave function is really a manifold, now we immediately understand that integers start playing a role also in the wave functions of the electron. And the reason for this is very easy. For example, if you think about the Euler characteristic of manifolds, for example, you know that the balloon, which differs from the torus, has an invariant that classifies it. And this invariant is the Euler characteristic, which is twice times 1 minus the number of holes that exist in your manifold. And this is different, of course, for the sphere than for the torus. So if somehow this wave function can be described by such an integer, then different integers would mean different states of matter, and that would mean a classification of the state of matter or of the compound that is basically as rigid as the periodic table of Mendeleev. Let me give you an example of such an integer. This is a very simple example where your wave function varies as exponential twice times the momentum. And you can see that as the momentum is varied from 0 to 2 pi, and the reason why the momentum is periodic, this has to do with some other piece of physics of band theory, but the momentum is really periodic. It can go from 0 to 2 pi. It's a lattice momentum. And this wave function, as the momentum goes from 0 to pi, you can see that its phase winds by 4 pi. So the winding of this phase in units of 2 pi is a topological invariant. And this topological invariant cannot be changed, for example, even if I took this curve and did a little, turn around here, moved it a little bit here, it cannot be changed unless I cut this curve and resolder it to make this invariant 1 or 0, for example. So it's a topological invariant that has to do with the overall topology of the curve rather than with small details of how this curve goes around. What are the effects of an integer like this? Well, you've heard a lot about topological quantum computing and the Microsoft Majorana 1 chip. I don't want to give you my personal opinion in a public audience about this, but the idea behind it is very beautiful, and the idea behind it is that these invariants, which are topological invariants, can basically sustain what's called topologically protected quantum computation. The gates of such a computer are basically braids or exchanges of particles as you take one excitation or one particle of such a topological state around the other. And because, as I showed you before, these integer invariants do not change whether you take it on a curve like this or you take it on a curve like this, whether you hit an impurity, you go around the impurity like this, or you go around the impurity like this, because they don't change, they're protected, then it means that these gates are protected, and it means that you can possibly do quantum computation with far less error correction than with normal methods. The catch here, so why is it so hard to realize this despite having a chip that writes Majorana on it? The reason why it's so hard to realize this is that to make a basic system that has these type of fermions, Majorana fermions, that allow for this type of braiding, you need two things. You need superconductivity and you need a magnetic field. And, well, you need some other things, but you certainly need those two things. Now, superconductivity and magnetic fields hate each other, and this is really the reason why these gaps in this material are very tiny, 30 micro electron volts, etc. So what we wanted really is something that, or experimentally at least, something that can be described by an integer, that is a material that doesn't exhibit this an effect when you add external fields, that is just being given to you as a material and is described by an integer, and that integer can classify the material. So basically for quarter century since von Klitzing's discovery, it was kind of thought that only under a magnetic field such things can happen. But as Paolo said, with the advent of topological insulators, it was immediately shown that just materials that can be made in a lab without any magnetic field or without any fields on them can exhibit topologically protected responses, or can exhibit a state that's macroscopically defined by an integer. And this integer really has to do with edge states. And in the topological integers, I'll get back to some other integers a little bit later. For example, in this mercury telluride quantum spin hole effect that Paolo mentioned, the integer is the number of edge states that are going in the left and right directions. They always have to come in pairs on the edge. If you have an even number of them, you're trivial. If you have an odd number of them, you're non-trivial. Now, in the modern bulk boundary correspondence, this is something that's true across the board, and it is in topological insulators. And for example, here you have a quantum snapshot of bismuth selenide. This is a snapshot of the electronic states of bismuth selenide. You can see here some blobs, which basically means that you're looking at the bulk of the sample. There's a lot of electrons here, so you're looking at the bulk. But the quantum snapshot is taken by cleaving the material and looking at the surface. And when you look at this surface, you see these edge states here, which are very clearly shouting at you. And their number, mod 2, is the topological invariant that describes this phase. Now, experimentalists were seeing this before topological insulators came about, and were trying to get rid of these surface states, okay, by just, putting things on the surface. They were unexplained, and they tried to get rid of them, and they found that you cannot really get rid of them. And this is because these integers really classify the phase of matter, and getting rid of these surface states really means doing something dramatic, not only to the surface, but to the bulk. Now, there's now many more examples. For example, this is an artist's rendition of bismuth, but bismuth, at least to the best of our knowledge, of experimental knowledge today, has edge states on hinges, rather, so it's a three-dimensional material. It doesn't have surface states on surfaces, but it's at the intersection of two surfaces, which are hinges. It has these electronic states. Now, the reason for that is because it's also described by a topological integers. Now, unlike previous eras of discovery, these topological insulators, theory predictions came before experiments. So the progress was, a lot of it was theory driven. And of course, just to give you an analogy of what these edge states look like, we can look at different examples of how topology would come in. Okay, so for example, in bad metals, or metals that don't conduct electricity or conduct it very poorly, you can kind of think of them as the streets of New York, I guess Cairo, and some other city, where basically you have both stop signs and many, many collisions between cars. Streets of Zurich, you have very little cars, but you still have stop signs and other cars coming in, so you still have some type of resistance to the electrons moving freely. In these topological insulator states, the edge states are basically separated by dividers. They're kind of like highways of cars, and highways move in one direction in one side of the highway, in the other direction on the other side of the highway. Now, there's no U-turns possible. The U-turns, if you want to make the U-turns, you're going to have to change the underlying integer that is protecting the state, or that's classifying the state. So that was the initial story of topological insulators and their edge states. But then, since 2010, it was realized that most of the materials can be described by topology, or a lot of them at least. Take the example of graphene, which is a hexagonal arrangement of carbon atoms that you can see it here. This hexagonal arrangement of carbon atoms is what's called a semi-metal. In other words, if you look at these electronic states, it has these nice Dirac nodes that high-energy theorists know a lot about. But if you look at the wave function of the electron, raising up a little bit the energy and trying to make a circle in momentum space here, if I look at the wave function of the electron, I'll see that it has a vortex in the center. And the fact that it has a vortex is very easily seen, because if I would move down here at the Dirac point, then you can immediately see that you'd have a singularity. And this vortex is basically the fact that the wave function winds as the momentum winds around the Fermi surface. The wave function also winds in a way that's not zero. So the wave function is not just a vector that's always zero, it just follows the momentum in this case. And that's the fundamental property of this Dirac note. It's a topological invariant of this metal in this case. Here I give you another type of material, and this material has these surface states that you can see here. This is energy versus momentum. These are bulk states, high density, but you can see surface states here. But unlike the surface states in topological insulator, these surface states are kind of dangling. They don't connect between the upper energy manifold of states and the lower energy electron manifold of states. They're kind of dangling here. And this is really the concept of covalent bonding, which since 2010 we really understand now as just an integer property. Let me walk you through this very quickly. Lattices, as you can see, for example, from this hexagonal arrangement of atoms, have symmetries. The symmetries of lattices are also described by integers. The reason why they're described by integers is that you have discrete groups, for example, 60-degree rotation here, that brings this, that leaves this lattice invariant. Well, not this one, but this one, for example, leaves this lattice invariant. Here's 120-degree rotation. And because of that, you have special points in your lattice. For example, this point in the middle of the hexagon is special because it maintains the entire symmetry, 60-degree rotation, some mirror symmetries. It maintains the entire symmetry of the point group of the lattice. These points here, which are the hexagonal points, which are the corners of the lattice where the carbon atoms sit, for example, have different symmetries. They have certainly a 120-degree rotational symmetry because this gets mapped here and this mapped here. And these sites here, which are called the 3C sites, they're the Kagome sites because their arrangement forms a Kagome lattice, and they have a different set of symmetries. Now, why is this important? Well, the reason why this is important is that this gives you a description of bonding that's based on integers, and that's not like in our chemistry lessons that we learned in high school, or at least that I learned in high school. It's exact. So when you talk about bonding with a chemist, they immediately know whether a material is covalently bonded or ionically bonded. But then if you probe a little bit deeper, it turns out that there isn't something very sharp that a chemist can tell you when this is covalently bonded and when this is not covalently bonded. However, physics and integers can tell you this. And the reason for that is the following, exemplified, for example, in graphene. In graphene, or in this hexagonal arrangement of carbons, carbon has sp2 orbitals, spx and py. These spx and py orbitals, they form an sp2 bonding, which is this covalent bonding. Because there's 3 orbitals here, in this sp2 bonding, I can move these orbitals away from the hexagonal site. There's 3 of them. I have 3 directions. I can move it away from the hexagonal site without breaking any of the symmetries of the lattice. So I can move one orbital or one electron here. I can move from this other site another one here, and I can bring them to the Kagome site. Now notice that this site here is a fake site. There's no atom on that site. Okay? Because there's no atom on that site, if my electron wave function, which is a quantum mechanical object, has actually moved here, I can count the number of electrons here at this site, or a number in condensed matter slang, the number of Wannier centers here. And if this number of Wannier centers is odd here, then it means I have no way of moving back to the original sites where atoms are occupied, and it means that my system is covalently bonded. And this type of an integer, which can be generalized to many more cases, gives you an exact definition of whether a system is covalently bonded or not. Now you can ask, why is this important? Well, it might not be terribly important to know that something is covalently bonded with a clear definition of an integer, but it certainly could be practical. So, for example, here is catalysis from Claudia Spelson group on MOS2. Now, MOS2 was known to be a good catalyst, okay? And the reason why it's a good catalyst was kind of mysterious, but the moral of the story of this material is that it doesn't have any electronic states on the surface, right? So it's one of these atoms where the Wannier center has moved. The Wannier center of the electron, one of these materials where the Wannier center of the electron has moved in between atoms. Hence, if I cut in between two atoms, which is, it means if I make a surface in between two atoms, I'll still have an electronic state there because the electronic state actually lives in between these atoms. This electronic state is responsible for the catalysis. Now, because of these integers, you can predict where you need to cut your system to get this electronic state. These integers tell you that my bonding, my covalent bonding has happened on this bond, or in between these bonds, or in between in the symmetry, in a given symmetry group, or in between some elements. In this material, you can immediately predict that your covalently bonded states will appear if you cut hinges, not surfaces. So you can clearly see here, if you look at the catalysis reaction of this material, that on surfaces, it basically doesn't have any catalysis, but on hinges, it has a lot of catalytic activity. So these are called real space invariants, for example. You can find them by some theory that's now very well developed. Now, to move the story forward, you can now go through the periodic table, click on some elements, then make your compound. You can see whether the compound exists. Now this compound, if it exists, is going to show up here. And then you can classify, you can go to the next page and see not only the structure of this compound, but see what the integers that classify it with covalent bonding or non-covalent bonding, with topology or not topology. You can see what classifies it as a set of integers that's given here. So, I hope to have convinced you so far that we can now classify at least some of the materials in this database of 300,000 materials based on integers. The actual number that come out with a non-zero integer is about 60 to 65% of them. Now, that's a huge number because it tells you that this classification of compounds by integers is not, as we thought at the beginning, esoteric or constrained only to mercury telluride or only to quantum Hall effects, but is something that's endemic in the materials that we have today. Now, what does the future hold for us? Well, I wanted to take you very briefly through what I think is the alchemy of today. Of course, there's many things that one can do in stoichiometric materials, but the power of integers and their application to materials will be, I think, very clearly seen in these two-dimensional materials that can be malleable and can be controlled by experimentalists to a higher degree, some of them, than the stoichiometric ones. So let me tell you what the alchemists of today are doing. Well, since the Scotch tape method of getting graphene, single graphene layers isolated, 2D materials scientists have basically tried to exfoliate van der Waals materials and then do something with the single layers that you get from these van der Waals materials. So how does a procedure work in this case? Well, the procedure works in the following sense. You basically take, in the case of graphene, you take graphite, you cleave it, you put an adhesive, you take basically Scotch and tape, you take single layers by just doing a lot of exfoliation. Then you can plant it on a substrate, and then you can take another layer, put it on top of the first layer, rotate it, not rotate it, and then you can add leads in different ways to the system and then start measuring. So let me show you what happens if you do this with 2 layers of graphene that you've exfoliated by doing the Scotch tape method. You take 2 layers of graphene and you rotate them by a small angle. So for example, these are the bilayer graphene, which is the twisted bilayer graphene, which is what Pablo Herrero was probably talking about here a few years ago. This method was invented by Emmanuel Tutuk, but basically what it does is it controllably takes 2 layers of graphene, and you can see the initial lattices of graphene that are these small unit cells here, and it rotates them by a small angle. And you can see what happens is that now you have a super periodicity at a much larger length scale. This length scale is of the order of nanometers or tens of nanometers. And it's basically, 10, 20, 30 times the original lattice. And you can see that this periodicity, called Moire periodicity, can stand in between the length scales of quantum chemistry, which are angstroms, and the length scales of optical lattices, which are microns. Because of this length scale in between these are not as malleable as the optical lattices, but they are more strongly interacting. Let me show you what such a material gives you. This is, again, twisted bilayer graphene. Starts off with single layers. You take them, you rotate them by a very tiny angle, which is around 1 degree here. And you can see this Moire periodicity forming. As you tune the angle, you get different Moire periodicities. Now, the remarkable thing about this is the influence of this twist on the electronic properties of this system. Single layer graphene has these Dirac nodes that I showed you before. These Dirac nodes basically have a dispersion, i.e. the electron energy goes from 6 electron volts or 3 to, so it's bandwidth of 6 electron volts, or 3 to -3. Huge energy dispersion. Now notice what happens here as you twist the angle and make it 1 degree. Notice this energy scale is milli-electron volts. So basically what you've done is tuned a 6 electron volt dispersion down 1,000-fold. Because you've tuned the kinetic energy down 1,000-fold by just taking these layers and twisting them, because you've done this, now interactions become important, and the interacting states of twisted bilayer graphene appear in this system. Interactions in this system of single layer graphene are not very important because this Dirac density of states here, as in known condensed matter, or number of states that you have at this cone, is very little. So you can get these Moire lattices, you can get these very flat bands of quenching the kinetic energy, you can get a lot of interacting states, as Pablo probably talked about it several years ago. But is this the only thing you can do? Well, no. In fact, there's about 9,000 computed 2D materials. There's about 500 of them that have already been exfoliated, van der Waals, or 200 of them that have already been exfoliated. There's about 9,000 of them that are computed by DFT methods. So now you can imagine taking these materials, exfoliating each of them, and putting one of them on top of the other in hetero bilayers or homo bilayers, then twisting the angle, then making 3 angles, then putting a huge number of them together and looking at the interacting states that come out of it. And you can say, well, this might be a theorist's dream, but it's not true. It's actually experimentally realizable. So for example, in the database that you have here, which is now clearly accessible by everyone on the internet, you can look at all these compounds. Some of them are already twisted and realized in 2 dimensions, such as molybdenum ditelluride, but most of them are new. In fact, only graphene and the molybdenum ditelluride and molybdenum tungsten diselenide, a couple of them have been twisted so far, so most of these are new. And you find out that every time you take a van der Waals sample, such as, for example, this one is SNSE, tin selenide 2, every time you take a van der Waals sample and exfoliate it, you're going to get single layers. Okay? You just do the Scotch and tape method. You then look with a microscope to see where you have single layers, and you're going to get single layers. So every time, for example, for all these materials that Claudia Felser and Leslie Shoup's grown, groups like Dima Efetov and Kim-Fai Mak and Xiao Dong have now exfoliated single layers of these. And once you do this, you can then twist them, and you can then realize flat bands or regions of electronic states with quench kinetic energy, which basically realize interacting states of matter. Now, these interacting states of matter, the interesting thing about them, coming back to the quantum computing, is that now you have a material that doesn't need any fields or applied fields on it, unlike the quantum Hall effect. So you have a 2D material that can exhibit, for example, superconductivity, magnetism, insulators, fractional churn insulators, which are the equivalent of this von Klitzing state, or a more complicated state than von Klitzing found, but with 0 applied magnetic field rather than with 30 Tesla. And if I just take 2 of these ingredients, superconductivity and fractional churn insulators, for example, you can get topological quantum computation and other things that so far have escaped us, at least in theory. Now, I'm not saying this is done, but it certainly brings you closer to having all these phases of matter on a single chip without applying many fields, many magnetic fields. So the last but one slide that I have is to basically tell you that there is, again, a catch. So you can say, well, you know, you have all these 2D materials, you can twist them, you can describe them by integers, by macroscopic integers that give you the properties of the states of matter. You can design Hamiltonians, you can have superconductivity, fractional churn insulators on a single chip, etc. So why don't we find the best material that can be found and do it? Well, the reason is that, as I said 2 slides ago, there's an embarrassment of riches, which in this case can only be probably solved by AI techniques. And this is not really just an AI pitch, but I really believe in this. If you take 2 of these materials and twist them, like twisted bilayer graphene or TMDs, the atoms won't like to sit at the rigid positions which were there before the lattice was twisted. The atoms will actually move, and this is called relaxation. And predicting relaxation is very hard because now your unit cell, or the number of atoms that live in this large moire cell, is basically thousands. So you have to predict where the atoms go in a system that, an engineer system, that has thousands of atoms per unit cell. Now, that's a process that if you want to do correctly, takes at least 6 months per choice of layers. And because, you know, you can have hetero, homo bilayers, tri-layers, etc., then the phase space of this states of matter, or of these electronic bands of predictions, becomes infinite. So only if you actually have something that can exponentially decrease the time that it takes to compute the relaxation of these samples and the electronic structures will you basically have, I think, a high throughput effort of finding many-body states or finding new physics in the system. Otherwise, you have to do it one by one, and that will be very time-consuming. So I reached the end of my talk. I hope I have convinced you that if you take integers seriously, you can find a lot of things in nature, possibly new materials. This has the potential to revolutionize humanity, hopefully. And the pitch of the AI has to basically, in my view, has to be that we should work with the AI to reduce the time necessary in this infinite phase space that we now have with the new alchemists of today that can twist materials at variable angles and make different types of layers, bilayers, tri-layers, where the phase space is huge. So thank you for your attention.
Thank you. I'm sure Andrei will be happy to take a few questions. Yes.
So for topological materials, besides the topological quantum computing, is there any other applications?
Very good question. So besides, for example, for the covalent bonding, finding out the surfaces where you can have catalysis, I think it's a good application. Okay, for there's people that are trying to do chiral catalysis on on materials that have to do with Weyl fermions, etc. Now, an actual application that's has revolutionized technology we don't have yet. So but that's, you know, that's sort of like asking for the, you know, transistor, right? For semiconductors, for the theory for band theory to immediately give you a transistor. That happens, the engineering part of it can take a long time. But I think at least, you know, a lot of stuff can come out of these topological concepts. For example, bounds on the superconducting temperature, right? We're so far, we don't really know if a room temperature superconductor can exist under ambient pressure, right? I think there could be situations where the knowledge that we have from topology, which is basically knowledge of Wannier states, of how spread out they are, of how, you know, these Wannier states interact with phonons, etc., could lead us to put bounds on superconductivity that are much better than, you know, the wrong bounds that were found before, and could save potentially a lot of time in looking for phase space, you know, for superconductivity in phase spaces where they might not exist. So I think, you know, at this point we're at an understanding level. If we're trying to find new technologies, you know, unless you believe in, you know, I mean, unless Majorana 1 is real, which might very well be very real, then we don't have something that I can, you know, give you that's a technology yet.
My question is about how is this to integrate experimental knowledge now to your periodic table of prediction and to try to identify now how close real life is from theory? Right.
So that's actually related to the previous question in some way. So it's a very good question. So I'll try to give you some, you know, as short as I can answer about it. So if you want to predict new materials, you know, this is just taking the materials that you have and classifying them. So this is not predicting new materials. Now, there's AI that predicts new materials, right? Which we know from right, Google and Microsoft, etc. And many people are trying to do it. Now, if you look at what that AI is doing, it's really not doing something very original. It's something that Claudia Felser or any other chemist could spot immediately, right? It's basically just taking some elements from, you know, below in the periodic table and replacing them, kind of the same reactivity element and replacing them, right? And this is what it does on superconductors, etc. So I think the main thing to incorporate into these material techniques to find new materials, the theoretical techniques, is some knowledge of symmetries and, you know, all of these AI codes don't have any of this in them so far. Any symmetries of the wave functions, etc., of the electronic wave functions, they don't have them in there. And then to understand, for example, why sample growers, once you predict even, you know, materials that have zero energy above the convex hull, so they should exist, sometimes most of the times they don't show up in sample growth. So understanding that experimental input is something that I think we should be doing as a community in terms of, you know, bridging the gap with AI finding new materials. So, and I would be very, very, growers have kind of like their own AI, right? Chemists and growers have their own AI in their brain that can tell you why this, you know, 20 materials that you've predicted with AI don't actually show up if you grow them, and that's happening a lot actually. So I think incorporating experimental advice is the only way to make material prediction work rather than like these high throughput things that people are doing right now. That's my view.
I'll ask a question myself before going to Steve that perhaps some people in the audience have in mind. So we live in this amazing new era of material discovery whereby you can make an entire family of materials simply by taking very simple materials and twisting them. Okay? So this seems to me to be a kind of adiabatic transformation. Yes, you have shown to us that, in fact, each of these different phases is described by discrete sets of numbers, sets of integers. How do these discreteness emerge from a continuous adiabatic?
Yeah, that's a very good question. So here's how they do it. So basically, you can see that, for example, just for twisted bilayer, I have a continuum of electronic states or a semi-metal in graphene. But now, once I start twisting them, I open these. You can see that here, these two bands have a gap. There's no states in between here and here. Because of Umklapp scattering and because of this new Moiré periodicity, you've created gaps here and here and here and here. And these two bands here, for example, in twisted bilayer, they have a topological invariant. They're actually topologically non-trivial, and this invariant gives you some of the things that you see in twisted bilayers, like Chern insulators. So the reason why, even though this angle is continuous, you can get this continuous behavior is because at some point of the angle, you're going to be opening and closing gaps. And that's where the change happens. But coming back to this prediction of AI, if I, graphene is particularly simple. But if I was to do another material, predicting where these gaps open and close, that would be a 6-month process just for the single particle electron. So for that, and for single angle or different angles, it would be very hard to do on a high throughput basis to understand the complexity of the phases, because I could have a gap opening and closing at 1.5 degrees, I could have another one in 0.9, etc. If I don't have something that's fast that will tell me what to do, because of this continuum parameter, we're going to be stuck in predicting in a fast way all the myriad of phases of matter that are likely to exist in these cases.
Steve?
Yeah, we've had more than a century now of discovering new superconductors, and it seems to me there are two phases in which that discovery works. First, you have a structure that you know is superconducting, and then you swap out different atoms to see if you can improve it. And we kind of know how to do that, roughly by trial and error. But the harder one is to find the structure type in the first place, and that's always been by accident, how they've been discovered. So with this approach of thinking about topological band structures, this insight you mentioned about covalent bonding is obviously hugely helpful. With those two processes, which do you think is going to be the more, this technique is going to help?
I mean, look, if you want me to be honest, I would still bet on the chemists and on the experimenters. you can't. That is 100 years of AI in their brains, right? Or more than that, centuries. So I would still bet on this. But I think, as you said, this replacing things by different elements and what the AI does that's not original, that's not very interesting, because that's just anybody can, right? I can look in the periodic table and just replace something. So an original thing would be a completely new structure, and that hasn't happened yet. But I think there's no reason why, if we put in, if we somehow get, I think at this point there's a disconnect between the people that are doing the AI and physicists and chemists with intuition. There's two kind of disparate communities, or maybe not very disparate, but there's certainly not been an effort, just because it's so new, to bring both of them together. So I think if you get, for example, experimentalists, chemists together with AI or neural networks people, etc., to predict new materials, I think something good can come out of it. I don't know how yet, but I'm pretty sure that something good can come out of it. For example, none of these neural network codes like Google, Microsoft, etc., they put in the symmetries of the some of them put in the density of states. They can obtain it from high throughput DFT, etc. But none of them actually put in the wave function symmetries, which are, those are the actual things that describe the phase. Density of states can be larger or small. Of course, they're all interconnected, but they're certainly missing some things that could be put in.